Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you for coming. My name is Kevin Coots, and I'm happy to welcome Charles Adler to the Microsoft Research Visiting Speaker Series. Charles is a professor of physics at St. Mary's College of Maryland, and he is here to discuss his book, Wizards, Aliens, and Starships, Physics and Math in Fantasy and Science Fiction. As we all know, science fiction and fantasy writers have come up with some brilliant and innovative ideas, but which concepts might actually happen and which wouldn't work at all? Charles will discuss these ideas and show the physics and math behind them. Please join me in giving him a very warm welcome.
Thank you all for having me here, and thank you for plucking me out of the East Coast ahead of the big storm. A great pleasure to be here where the weather is much nicer than it is out there. I'm going to talk to you today about the ideas of science in science fiction. And the issue is the connection between science and science fiction is sometimes close and sometimes fairly distant. Now, if you think about science fiction, it's fiction. It's not science. If it were science, it would be a PBS special rather than a movie or something like that. But I think, though, that a lot of writers and especially movie directors have this idea that science fiction basically means, because we're thinking about all these fantastic things, alien life, space travel, other things like that happening in there, that a lot of people who write these books have this tendency to think, and maybe a lot of viewers as well, that essentially science fiction means anything goes. And I would like to challenge that idea right now. I'll start off with a nice example from a recent film. This is from the film Star Trek Into Darkness. We see here a scene where Sherlock Holmes, John Harrison, a.k.a. Khan, is viewing a scene of mass destruction here, which he's just caused on Earth. And then just immediately after the scene, we're not quite sure what's going on, all of a sudden the scene shifts and he vanishes. What's happened here was that he used the transwarp effect to transport himself immediately from Earth to the main planet in the Klingon Empire. When I was watching this movie, a couple of things started going through my head at this point. First of all, I want to repeat the issue here. Science fiction doesn't mean, a science fiction story does not have to adhere to all the laws of science. It can't, or it wouldn't be fiction, it wouldn't be science fiction. But I will make this point that I think we have to expect the authors of the story, the writers of the story, to play fair. We must expect them, if they introduce something like this transwarp effect, to think about the implications that it has for the rest of the story. Now, here are a couple of things that came to my mind when I was thinking about this transwarp effect here. The first one, and this is because I'm a physicist, is the issue of precision. He just transwarped himself across a distance of light years, many light years to another star system, and distances like that, in miles, we're talking about something like 50 or 60 trillion miles, assuming that the Klingon star system is one of the nearest ones to our own sun. Stars are light years apart, they're trillions of miles apart, and he transwarped there with a precision of a few feet over the course of trillions of miles. By my estimation, that's about 1 part in 50 quadrillion accuracy in terms of doing that. If you think about that, knowing the Earth's diameter the same precision would be knowing it to the precision of the diameter of an atom. Okay? So he's transferred. Now, this is not to mention any of the other problems associated with the idea, okay, well, the two planets are moving, we have to match distances, things like that. But, okay, that's really big accuracy. It's a really high degree of accuracy. All right, but let's move on from there. Now, another part of this is, of course, the Federation has starships. If you can do this, why do you need a starship? If you can transport yourself instantly through anywhere in known space, you don't need a starship. If you've got something, starships are big and expensive looking, and they're slow, at least compared to this. This supposedly looked like it happened right at once. If you can do that, why do you need starships to begin with? Why isn't just everyone going everywhere using this transwarp device? And of course, a large part of the plot of this hinged on the idea that they had to send the Enterprise out to there to retrieve this guy Harrison because he transwarped the Klingon Empire, and they're worried that the Enterprise is going to get involved with the Klingons and start a war because they're worried about the Klingons. Well, given the transwarp thing, this transwarp effect, you do not need to worry about a war with the Klingons. If you have this device and the Klingons don't, and the Klingons start making problems, you immediately transwarp an antimatter bomb to their planet, and you've solved the problem. If the Klingons have it as well, that's a little bit different. But still, you know, it didn't make a whole lot of sense. And so I think that the movie is bad science fiction in that sense. Science fiction is supposed to be a literature of imagination. The idea of what happens when we apply advanced scientific ideas to the ideas of literature. But again, the authors have to play fair. One of my favorite science fiction authors, and the man to whom this book is dedicated, was Poul Anderson, a quote-unquote golden age science fiction writer. He wrote at the same time as Heinlein did, Isaac Asimov, things like that. He wrote an essay called How to Build a Planet, which this book would not have been written without my having read this essay before. And in the book, he made a point: the process of designing a world serves up innumerable story points. The essay was essentially on how to design a scientifically realistic planet for the settlement of alien life. If you can find the essay, it's not easy to find anymore. I would highly recommend reading it. The point, however, is that if you constrain yourself to be self-consistent and to work with science that's, at least kind of plausible, it makes for a much stronger storyline than if you kind of get away from all of that. And the best science fiction writers pay attention to these ideas. Now, I will say one thing, however, that not all the laws of nature are equivalent to one another. Scientists tend to kind of rank them. And I would make the following statement, that if you look at the ranking of the laws of nature, the ones that come at the top, and the ones that science fiction writers tend to stress the most and pay attention the most to in their stories, are what I would call the great conservation laws: the conservation of mass energy, the conservation of momentum, the second law of thermodynamics as well, and the principles of relativity, although science fiction writers tend to bend them to be able to go off to distant star systems relatively quickly. But I would say the great conservation laws are the ones at the top of the list, that science fiction writers who are paying attention to the science will tend to focus on. And so for the next section of the talk, I'm going to actually just focus on one of them. My book goes through more of them. I call this section, for reasons which will become obvious in a second, Harry Potter and the Great Conservation Laws. Now, I like taking a look at fantasy as well. Right up there, you have the most famous formula in all of physics, E = mc squared. It is a statement that mass is a form of energy. Mass is equivalent to energy. And so we can convert energy into mass, or vice versa. Now, if we look at the conservation of mass energy, we run into some interesting issues. We want to look at, say, the Harry Potter films. Mass, let's say we're looking at the scene from the first film where Professor McGonagall goes from Professor McGonagall in the Harry Potter books is an animagus. She can turn herself from a human being into a cat and back again. Cats weigh a lot less than human beings. I've known some which were kind of an exception to that, but most cats weigh a lot less than most human beings do. And so if we think about this issue of Professor McGonagall turning herself into a cat, well, E = mc squared basically says that, for every kilogram of mass, there's a lot of energy involved here. If we look at the amount of energy that it takes to, that she will liberate by turning into a cat, we arrive at, again, fairly E = mc squared. It's a simple formula to do. We get that she liberates something like 50 H-bombs worth of energy every time she turns from a human into a cat. Hogwarts, boom, right, at that point. Now, this is fantasy, so maybe we'll give a little more leeway to Ms. Rowling because, for use, it's fantasy. It's maybe not quite so nice. Although there are some fantasy writers who actually do pay attention to the conservation of mass in fantasy stories, Poul Anderson being one of them. But, we'll let her slide on this one. But when we go back to science fiction, there are actually a couple things I would like you guys to consider for a second. We know that the Starship Enterprise is powered by matter-antimatter reactions. And if we look at that, well, antimatter is kind of hard to find. It doesn't really occur in the real universe in very large quantities. If we want to make antimatter out of nothing, which can be done, we do this in reactors all the time, as just flashed by there, the energy cost is 90,000 trillion joules per kilogram of antimatter. So we want to make this. We get a big power plant. We run in some sort of accelerator. We start generating the antimatter. We'll worry later about how we confine it. Okay, so we do this. At current energy costs, that's $3 billion per kilogram. $3 billion per kilogram if we could do it at 100% efficiency. We cannot do it at 100% efficiency. At best, the laws of physics will let you do it at 50% efficiency. But in fact, realistic studies have been done. Robert Forward actually did some studies about it and came to the conclusion that if we at current technology, you could do it at an efficiency of about 0.1% to 1%. So we're actually talking about energy production costs thousands of times larger than that, hundreds to thousands of times larger than that, for realistic technologies available today. So maybe in the future, in the world of the Federation, they'll bring it down. But it's still going to be a costly thing. And the Enterprise is going to need a lot more than 1 kilogram of antimatter to power it, possibly thousands of kilograms or even more than that. Another issue comes up, though, concerning this. If we go to Star Trek: The Next Generation, probably my favorite version of the show, if you remember, there was this thing called the replicator, I think it was called that, where Captain Picard would stand next to this little box in his office and say, "Tea, Earl Grey, hot." And somehow a glass of hot tea would be beamed into this little box sitting there. Now, presumably, this is an offshoot of transporter technology, or something like the holodeck, right? The holodeck materializes these things. And so, presumably, you're materializing a cup of tea from pure energy. We've discussed the issues of energy costs in the last, but I want to point out one other thing, though, which is that there is no technology that is 100% efficient. Technologies always involve a little bit of waste heat. So let's assume that the technology behind this device is 99.9% efficient, which is much, 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 much better than any available technology on the face of the Earth. If we do that, assume 99.9% efficiency, we find that, okay, we materialize this, we've got a lot of waste heat being generated, enough to brew 2 billion cups of tea with the waste heat generated by creating 1 cup of tea from this replicator device. I'm not sure why we're doing it this way in the first place. I guess it looks cool, but still. Now, you may say that, okay, well, you're spoiling all the fun of these stories. Why are you doing this, man? And the thing I got to say back is that this is all part of playing the game. If you look at, people do a lot of literary criticism of novels. What I'd like to talk about is the scientific critique of science fiction. It doesn't spoil the story to have these things in there. Okay, at least, well, I will say that Star Trek Into Darkness was kind of spoiled because of the other issues. But it doesn't have to spoil the story, not worrying about the science here. On the other hand, I would say it adds an extra dimension to the story to actually think about the science here and whether it's scientifically plausible or not, and about the things in the story that are plausible and aren't plausible. I think it adds an extra fun to the story, and it also, I think, gets you thinking about this sort of far-out science and things like that. So, going on, I like doing it. It's fun for me to do it. I hope everyone else finds it fun as well. Moving on from here. let's talk about this issue about, the Enterprise is, of course, concerned with going out, seeking out new civilizations, finding advanced life forms. So let's talk about this issue in science fiction of space travel. It is pretty clear that if you read science fiction, if you go back far enough, back to the 1950s to the 1980s perhaps, the future as envisaged by science fiction writers is not much like what we actually got today. Here is a book cover from Robert Heinlein's 1949 juvenile novel, Rocket Ship Galileo. It is a great book. I love the book. It's a book based around, the first trip to the moon, back in 1949. And it's actually it's a fun read. It has in it Boy Scouts who build this spaceship to go to the moon. It has an atomic-powered spaceship in it, the Galileo. And they end up fighting Nazis who made it to the moon before then. What's not to like about this? The Nazis have actually made it to the moon before them. They've established this moon base. They're going to bomb the rest of the planet, back into the Stone Age because they lost the Second World War. But our future today looks nothing like what Heinlein posited. We've put people on the moon, of course. We put them back in the 1960s. But we haven't really gone back there since the early 70s. And Heinlein and most of the other writers like him assumed back in the 1950s to the 1970s, and you can actually see essays they wrote talking about this, that in the future world of the 1980s through 2000, people would be routinely involved in space travel. Space travel would be cheap and easy. Lots of people would be out in space. If you've seen the movie 2001: A Space Odyssey, you get the idea of what all of this is going about. So what the heck happened? Why did we not get this future with cheap, easy space travel? Well, I think if you look at it, what happened was that there's an interesting combination of things that the science fiction writers got right, but also got wrong. What they got right was the science. If you look at Rocket Ship Galileo and other works around the same era and other works by other science fiction writers, the science is pretty darn good. Heinlein paid attention to the science. He was what is called a hard science fiction writer. He paid attention to the science. He made the rocket ship scientifically plausible. He anticipated the atomic energy rocket program by 20 years. The U.S. had an atomic-powered rocket ship program called NERVA, which ran from 1972 to 1975. They originally considered it for the NERVA rockets for the Apollo program, but they decided on chemical engines at that point. So it was good science. He understood the physics of getting a rocket from the Earth to the moon. However, it was bad accounting. Heinlein and other science fiction writers like him made the assumption that the ultimate costs for space travel were going to be the costs involved in the fuel. The fuel costs were going to be the driving cost for the mission. And if you look at that, and if you look, even today, if you look at the space shuttle missions cost something like $400 million per mission. Fuel costs for the missions were only something like 1% to 10% of the total cost of the missions. They were not the driving costs. The accounting that took place, the bad accounting that went involved here, was that the science fiction writers really grotesquely underestimated the other costs associated with it, the overhead costs. The fact that for any mission going out into space, you need buildings, you need trained personnel, you need to hire engineers and computer programmers, you need to hire people who are going to train the astronauts for their missions. You need a huge support program to actually support the people going off into space, which they completely ignored when they actually looked at the fuel costs. The fuel costs are just kind of the minor point of it. But what they also ignored was another issue as well, which is almost uniformly science fiction from this era has no computers. Or at least the computers that they have in this era, well, if you remember back to 1960s, computers were these big machines that you had in rooms. My father was a computer programmer for the State Department. I visited him there. And again, my impression of a computer back then were these big machines that were in rooms that you typed on teletype machines, to communicate with. No one back then anticipated the millionfold shrinkage in computers and technology, okay, which people, which is a very common part of life today. People expected that science fiction writers expected that manned programs in space would be the most important part of the space program. Scientifically speaking, they are not. They're actually a fairly minor part of the space program because it is infinitely easier to put a computer up there than it is to put a person up there. You don't have to keep them alive, among other things. The overhead costs for people are probably 100 times higher than putting a computer up there, and there are very few things that a computer can do, that a human can do, that a computer cannot in space. This is why, in fact, most of the really important scientific missions have all been computer-driven. Okay, now, of course, let me back up for a second. I think that if you look at it, right now, as far as human space travel goes, I'm not saying that there's no role for humans in space, but what I will say is that as far as human space travel goes, we are something like where Charles Babbage was. Babbage was the inventor, one of the first people to try to invent computers back in the early 1800s. And he had these designs for this huge machine, the analytical engine, which was this computer that would work off of steam, a steam-powered mechanical computer. And he had these designs, and it didn't quite work. It was marginally a workable operation. It was never built. It was very, very expensive. But he was not able to see the revolution that we had in terms of the electronic revolution. The revolution of transistors and chips and things like that have gone on to make the world that we know today. I think that in terms of space travel, we're somewhere like that right now. We don't have manned space travel except for the extraordinarily rich. People can shell out about $20 million apiece for space tourism today, but it's not going to come down until something like that happens. Now, one of the truly audacious ideas that has been proposed for actually bringing the cost of space travel down is the space elevator. It is exactly what it says on the box. People have had this idea of building an elevator into space. The idea being, it's this very straightforward idea. It actually dates back to the 1880s. It's a lot older than people think. You put a satellite in orbit around the Earth in a geosynchronous orbit, like our Dish Network satellites or whatever, for satellite TV. Stays in the same place over the Earth, rotates around the Earth once every 24 hours, the same as rotation period of the Earth. You then start elongating it. You start pulling part of it down and pulling the other part of it up so that the center of gravity stays in the same point always. And you pull one end of it so far down that that end touches the Earth, and the other one extends more than twice as far out, up going the other direction. And people have proposed this as a means both of lowering fuel costs and lowering other types of administrative overhead costs for this. Now, I am a space elevator agnostic. I will make that statement right now. I think it would be wonderful. I would love to do it. But I want to point out a couple things about it. The book actually addresses some of the materials problems. We don't have any materials. We are kind of borderline on having materials that could actually build the space elevator nowadays. People want to build them out of these carbon nanofibers, but no one's been able to actually make really long lengths of them yet. They are materials that are really, really strong and really light. You're talking about this 150,000 mile long structure here. So it's got to be really strong and really light. But I do want to make a point, though, about building a structure like this. The enthusiasts want to build it in the next 30 years. Okay. Well, through ancient times, up to around the year 1900, the tallest structures in the world were about 100 meters high, 300 feet high, roughly speaking. And that's because of the materials that were available, stone. Try to build something much larger than that out of stone, you run into problems. In 1900, or around 1900, Eiffel constructed the Eiffel Tower, which effectively doubled the size of all buildings ever built up to that point by building it out of steel. Steel structures are better than stone structures in terms of their strength-to-weight ratios and things like that. And so he built this very high structure, the Eiffel Tower, which was basically twice as large as any other building built up to that point. And we've gotten better than that. Our structures today stand maybe twice. The tallest structures in the world today stand, I think it's about twice the height of the Eiffel Tower does. Maybe more than that. I'm not 100% sure. But they're 2-3 times the height of the Eiffel Tower. Not a whole lot bigger than that. Well, the space elevator would be 150,000 times larger than the largest structure on Earth. The issue is we have to go from structures which are like the skyscrapers, structures as tall as the skyscrapers, to things that are 150,000 times larger in 30 years. I think that it is safe to say that we actually do not understand the engineering problems involved in constructing a structure like that. If we tried to build a structure like that, we were going to run into problems we have no concept of today. Not to mention that the space elevator would represent a structure unique on the planet today. If you think about it, structures on Earth, all structures resting on the Earth, are structures which are built either in compression, being pushed down, or in tension, being pulled out. Okay? Stone structures are mostly built to withstand compression. Steel structures are built as a combination of both to resist both compression and tension. The space elevator is only in tension. It does not rest on the Earth. In order to stay in the heavens, basically, the part that hangs down from it, gravity overwhelms centrifugal force, and so it gets pulled out. The part above the center point, centrifugal force overwhelms gravity, and it again gets stretched out. We have never built any structure like this for that reason as well. And so I tend to think that it's going to present a lot of interesting issues. It's a wonderful design to think about, but I think it's going to present a lot of interesting problems if we actually ever try to make the structure. And again, like I said, I think it's kind of on the borderline of possibility, but I'm not entirely sure which side of the border it's on. Okay, let's keep on going. People have called for President Obama and the other past administrations have called for a manned trip to Mars. I think the timeline is something like 30 years out now, of that order. I want to discuss a little bit about what that would involve with present technology. People have called for it. We've landed unmanned missions on Mars. That, by the way, that's a quote from one of Robin Williams' albums. I just love it there. People have called for manned missions on Mars in the next 30, 40 years, something like that. Now, I would like to discuss some of the issues involved with a manned landing on Mars. We put people on the moon, right? So how hard could Mars be? Well, I want you to think about the scale here. The moon was 230,000 miles away, 240,000 miles away from the Earth. Mars, at its closest approach, is 78 million miles. So hundreds of times farther away. Now, the point is that that's at its closest approach. And the point is that if we were to send a spacecraft out there today, we would actually not have Mars at its closest approach when we sent the spacecraft out. The reason being is that when we actually start talking about trips beyond low Earth orbit, or trips beyond the moon, or things like that, fuel costs do start to get very expensive. And so we want to look at the orbits that take the minimal amount of fuel. The orbit that takes a minimal amount of fuel essentially would be sending the spacecraft into orbit around the sun. So it would be an orbit around the sun just like another planet orbiting the sun. It would follow the same laws of orbital dynamics that the Earth did. It turns out that the minimum energy orbit, let me just demonstrate what that looks like here. The minimum energy orbit starts when the Earth is on one side of the sun and stops when Mars is on the opposite side of the sun. It's called a Hohmann transfer orbit from the German engineer who first thought of it. And it turns out that this is the orbit which takes the minimum amount of energy that it requires to travel between these two planets. Now, the issue here, of course, though, because it is in orbit around the sun, just like another planet around the sun, one can use the principles of orbital dynamics to work out how long it takes. It's actually pretty easy. I won't go through the details, but if you actually work out the case for Earth and Mars, it takes about 7/10 of a year, 250 days or so. And we've done it before. We've put spacecraft onto Mars, unmanned ones though. If you think about the problems involved in putting human beings out to Mars, you start thinking, oh, well, they're going to be in space for 250 days going out there, but they can't come back immediately because Earth and Mars are in the wrong position. If you want them to come back, well, you have to wait, by my calculations, something like another 6 months before you can actually send them back to Earth. And of course, you have to store all the fuel you're going to need. Well, actually, I think people have talked about putting fuel along the way. But the fuel costs are pretty big, especially for bringing human beings back. To give you an example, when you talk about fuel, you typically talk about mass ratios. The fuel in a spacecraft is usually a lot more than the mass of the payload. For example, the mass of the rockets that took the spacecraft, the mass of the shuttle engines, I think, is something like this mass of the shuttle propulsion is something like 20 times the payload mass of the space shuttle was. So for Mars, let's say we're talking about the same thing, 20 times the ratio. It's going to be bigger than that, but let's just say, for the sake of argument, that's that way. So 20 times the payload mass goes into fuel. That's for the trip out. The problem is that in order to take all that fuel out with you, that's for the trip back. If you want to go back, you have to, your payload mass is going to be 20 times your thing. So you're getting back from Mars, your spacecraft initially starts out 20 times the mass that's actually delivered back to the Earth. The issue is that to get out there, you need to actually bring the spacecraft out with all the fuel you're going to need to get back. So the payload mass has to be multiplied by another 20. The payload mass suddenly becomes 400 rather than 20 because you've got to get these people back. Of course, there have been calls for people to colonize Mars, go out on a one-way trip. There are some people I suspect would be willing to do that. My own feeling about that is that it's probably more like a slow form of suicide than almost anything else, all right? I don't think that one could actually do that in good conscience to people who are wanting to go out there. I will say this, though. If we could build spacecraft, which were not limited by these fuel costs, then the universe is our oyster. Let me give you one example. Very simple, straightforward thing to calculate here. If you were somehow to be able to build a spacecraft that could accelerate with 1g acceleration, you're on the spacecraft, you're traveling through space, the spacecraft is continually traveling faster and faster and faster. If you could build one that could travel with the same acceleration as the acceleration of gravity, so that every second you're moving 32 feet per second faster than the last second you're moving in. So it keeps on speeding up, speeding up, speeding up. You have to keep you have to keep the accelerator on all the time, but okay, we'll worry about that later. If you could do that, how long does it take to get to Mars? It takes 250 days in the last calculation, but if you could just accelerate there all the way out, with an acceleration equal to the acceleration of gravity. Anyone can do that. If you can stand up, you can survive that trip. How long does it take? It took a few months for the other trips. It'd take a month. It'd take a week. Amazingly enough, at constant 1g acceleration to get to Mars at its closest approach, 2 days. If you can accelerate at 1g continually for a long time, by the way, that calculation assumed that we flip around somehow and decelerate to slow down and stop by the time we get there. If we can do that, then it only takes a few years to actually get out to the nearest stars. Now, if we start doing that, of course, we run into this one problem, which is that as far as we know, the speed of light is the ultimate limiting speed for the entire universe. And so when you keep on accelerating like that, you're going to be pushing light speed fairly quickly after a year or so. When you start getting close to the speed of light, you have to take into account things like the theory of relativity. Turns out that it's good for you, though, because the theory of relativity tells us that our clocks aboard the spacecraft start ticking away more slowly than they would on Earth. Because of this, you can do this amazing calculation which basically tells you that at constant 1g acceleration, you can actually get to the edges of the universe within a human lifetime. It takes about 40 years, as measured by your clock on the ship, to travel about 1 billion light years. I find that just incredible. I love relativity. I think it's one of the neatest things in the world. If you could do that, you could get anywhere in the universe within a human lifetime, or at least a lot of interesting places within a human lifetime, if you can do that. Yes?
Would the universe expand?
Well, oh, right. Yeah, I'm not worrying about that, right? Yeah, it would keep on expanding while you're going out, so maybe not anywhere, but...
Everyone you know be dead?
Oh, yeah, everyone we know would be dead. Yeah. It would be billions of years would pass on Earth, yes. Yeah, billions of years would pass on Earth while you went out gallivanting like this. There are science fiction writers who have written about this. Poul Anderson, again, wrote a neat book called Tau Zero, which is basically premised on that idea, that essentially the spacecraft has to keep on, I'll go into it later on, but it basically is the same idea there. But yeah, everyone you know is long dead. But yes. But, if you want to go out and explore, I can see the appeal of it. There is one little problem, though. In 1961, a physicist named Edward Purcell did a quick calculation of how much power a spacecraft like that would take when it took off. You run into a problem, which is that if you take off anywhere near the Earth, you basically are irradiating the Earth with the same amount of radiation that the sun illuminates the Earth with, but all in the form of high-energy gamma rays. You essentially sterilize the planet. And this is for fairly reasonable sizes of spacecraft here. It's actually a fairly straightforward calculation to do. And so you can't take off with the spacecraft anywhere near the Earth, okay? Because you basically destroy the Earth by taking it off. I'm going to make a point about this, though, which is, I think, something you should consider when watching science fiction movies. Anyone here remember the science fiction movie Avatar? It came out, I don't know, 5-6 years ago, something like that. At the end of Avatar, the Na'vi are triumphant. They've won the war over the human beings. They send them all back to Earth on their spacecraft. That was a very bad idea. Larry Niven was the first science fiction writer to point out that any spacecraft, any starship, because of the enormous energies implicit in its design, makes a darn good weapon. The Earth people, merely by turning on their starship's engines, their starship can travel 2/3 of the speed of light, by turning on their starship's engines, can sterilize the planet. And they can go back in and get all the unobtainium they want after that point. And the Na'vi, who are a Bronze Age culture, can't do anything about it. They can't get access to the spacecraft. So I think these points are interesting, because when you start thinking about these things, there's no way the Na'vi should have actually let them get anywhere near that spacecraft after they won the war on the planet. All right. Of course, if we want to build spacecraft like this, we have to have actually some reason for building a spacecraft like this. And so that kind of forms a natural way to get into the next section of the talk, which is, of course, one of the big reasons for going out there is the issue of the communication with alien life. We live in the golden age of exoplanet discovery. One of the problems of writing this book was that I expected that any time I would write anything down about discoveries of planets outside of our own solar system, it would be outdated in a week. There are scientific programs right now that are continually finding new planets outside of our solar system. The planets inside our solar system are now in the minority by a huge margin, 40-1 at least. We know now 40 times at least as many planets outside of our own solar system than we know inside of it. And of course, the golden ideal here is to find an exoplanet with life on it. Okay, that's what we really want to do, find an exoplanet with life on it. All right, so the question is, what are the criteria for life on another planet? To start out with, I'm going to talk about this in terms of a physics sense. Okay, I'm going to talk about the physics involved here. I'm going to go through what I, in the book, somewhat immodestly called Adler's mantra, which is something I tell all of my astronomy students the first day of class. The mantra goes like this: all stars are the same. This does not mean that all stars in the universe are like our sun. But what it does mean is that all of the stars in the universe, all of their properties really depend only on one thing: their mass. The mass of a star determines its surface temperature, its lifetime, the amount of light that it emits. Almost any property you want to know about the star is essentially implicit in that one parameter, its mass. The stars are very, very, very similar objects to one another. Planets, on the other hand, are a chaotic mess. The issue of planets are kind of the schmutz left over when solar systems form, the little dandruff left over once the star is formed. The star, of course, is something like 99+% of the mass of the entire system. When the planets form, they form essentially out of whatever's left over, and they form rather. There are common features that the planets have, but their diversity, I would say, is actually at least from the point of view of talking about life on other planets, their diversity is at least as great as their commonalities. For example, Earth is the only known planet in the universe, to the best of my knowledge at least, which has plate tectonics. There is evidence that Venus had plate tectonics at some point in the distant past, but it probably doesn't have it anymore. There are a lot of things that determine what a planet is like: geological history, history of impactors, things like that, that actually make all planets strikingly different from one another. What I'm going to state, however, is a third thing, which is an unproved hypothesis on my part, which is that when we actually find life on Earth like planets, they are all going to resemble one another in a large number of fairly striking ways. A lot of them, in fact, a lot of criteria we actually probably don't know ahead of time. This is what I would call, this is an example of what Jared Diamond, a sociologist at UCLA, calls the Anna Karenina hypothesis. The opening line of the novel Anna Karenina stated that all happy families are the same, all unhappy families are very different from one another. The issue here that he made was that all happy families have to get a lot of things right in order to be a happy family. No money trouble, parents who love each other, kids don't talk back, things like that. All unhappy families mess up in one or two of these areas, but there are a lot more ways to mess up than to get it perfectly right. What I would say is that for Earth-like life to be on a planet, Earth is in some sense, I would say, a cosmic lottery winner. In order for Earth-like life to be on a planet, you probably have to get a lot of factors correct. And if any one of those screws up, you're probably not going to see life on the planet. And again, we probably don't know all the criteria that are involved. Now, the most important point, I would say, from a physics standpoint, is that the planet needs to be neither too hot nor too cold. This is basically called placing the planet within the habitable zone, a zone of life near the star, which is neither too close nor too far from the star. So let me discuss a little bit about what's involved in finding a planet within the habitable zone. Oh, darn it. Back up for a second. All right, this is an example of Earth. The issue is the habitable zone is dependent on the amount of light the star puts out, the luminosity of the star. If the star is like our sun, I'll call the luminosity of our sun equal to 1, and the distance of Earth from the sun equal to 1 as well, the average distance. If the luminosity is 1, we want the planet to be about the same distance as Earth is from its star in order to see the same illumination from the star. And the illumination, in some sense, is going to determine how cold or how hot the planet is. It's actually a pretty straightforward issue if you want to actually find how far planets need to be in order to get the same illumination that Earth gets. If we want the planet twice as far away from the star should be 2 times 2 brighter than our sun is, a luminosity of 4. It should be 4 times as bright as the sun if we want the planet twice as far away from, if we want the Earth-like planet twice as far away from the star. And the rule is, again, very simple. If you want the luminosity to be the same, take the distance of the planet from the star and square it and that's your star's luminosity. It goes that way because the illumination of light drops off as the inverse of the square of the distance from the star. Again, 3 times as far, 9 times as bright. Except, you run into some complications involved here in that illumination isn't the only thing. This is a picture of the planet Venus. The planet Venus, because it has an atmosphere primarily composed of carbon dioxide, well, Venus might have been marginally within the habitable zone of our solar system. The problem is that because its atmosphere is 95% carbon dioxide, there is a runaway greenhouse effect on its surface, which makes the surface hot enough to melt lead. So there are complications that run in here. Now, the other issue, of course, is that placement inside the habitable zone, well, there seems to be a feedback effect here going on for Venus. Venus started out with carbon dioxide in the atmosphere. Because a little closer to the sun, it heated up a little bit more, driving more carbon dioxide out. More carbon dioxide in the atmosphere led it to further heating, leading to more carbon dioxide being driven to the atmosphere. And a weird feedback effect is going on there. It would seem to have gone on there when to make Venus in fact, that hot. There are actually further complications as well. And again, there are more criteria than that. There are further complications as well. If we look at the position of the sun within the Milky Way galaxy, some astrophysicists have speculated that, in fact, there's a habitable zone inside the galaxy as well. The issue here, of course, is that if you get too far away from the center, the stars are low metallicity, meaning that they're mostly hydrogen and helium. They don't have as many metals as our sun does. And having quote-unquote metals is actually favorable for planet forming. Get in too close, there are too many supernovas forming these higher element materials, and the radiation may be too intense for life to form. Again, we don't know. People actually do not know whether that's a correct hypothesis or not. But again, there may be all sorts of different criteria for this. And again, we probably don't know all of the ones. Now, the one issue here, of course, is that we actually want to find intelligent aliens. We want to talk with the other guys. Even if we can't go out there, we can actually communicate with them via radio. You can actually detect radio signals from Earth, probably over a distance of order several light years. I think maybe even as much as 100 light years away. However, our technological civilization has had radio for the last 100 years, meaning that we would not be able to communicate with anyone, or no one would be able to detect us at least, who's farther than 100 light years away from us. Well, 100 years is not a very long time in terms of the history of the cosmos. The history of the cosmos runs billions of years back. Intelligent life could have formed any time within that period. A miss is as good as a mile here. If they evolved and then stopped having a technological civilization 100 million years ago, we would never learn about them because we were too late. If our civilization ends 1,000 years from now, and intelligent aliens involve 10,000 years from now in another star system, they will never hear of us because we evolved. We went out of existence too early. I'll give you an analogy about this. Imagine being in a dark field on a warm summer's night, everything around you dark, and you look at fireflies coming through here. And you watch the fireflies wink in and wink out. You'll see one. There aren't that many fireflies around. You'll see one wink in, wink out. A little while later, another will wink in and wink out. Occasionally, two will wink in and wink off at the same amount of time, in the same time. But, a lot of the time, you'll just see one flickering on and flickering off. This is, I think, the situation which we are with respect to alien life in the cosmos. If the lifetime of a civilization isn't long enough, if the lifetime of a technologically advanced civilization isn't long enough, then there's very little hope of actually detecting other intelligent alien life. We don't know what that is, of course. People like Frank Drake, in his famous Drake equation, have actually tried to estimate this. I would say that if you actually look at the geometry of the Milky Way galaxy, that if a civilization is not going to last for several thousand years at a very, very, very base minimum, then there's probably almost no hope of different alien races communicating with one another. It's kind of a depressing thought, but I suspect that that's actually probably a fairly decent minimum idea. Now, the question, of course, that does beg the question, of course, how long can, in fact, an intelligent civilization last? And let me just discuss that very briefly. An advanced technological civilization last. There are, of course, obvious problems going on in the world today. Right now, we face major problems with our civilization. Over the next century, we're going to have to deal with the issues of both resource depletion and global climate change. These are going to be pretty serious problems facing us. They could, in fact, mean the end of our technological civilization. If we make it that far, make it for a few thousand more years, of course, we have to worry about the next ice age, or actually really the next period of glaciation. The last glaciers were treated something like 20,000 years ago. And if you look at all of human history, the last 5,000 years is from far beyond the point. Recorded human history from 5,000 years ago is far beyond the point that the glaciers were treated. Agriculture developed when the glaciers were treated, probably, probably because people had a fairly nice, relatively stable climate to grow crops in. When the next ice ages come back in 20,000 years or so, will human civilization survive them if we're still around at that point? I hope so, but it's going to be a big change. We had glaciers covering, I think, a mile thick in Wisconsin, in the last one. If we go beyond that, we of course have to start, if we start thinking really long term and making the civilization last even longer term than that, we have to start thinking about things like, 65 million years ago, an asteroid impacted the Earth, destroying all the dinosaurs. They happen, once every 50 to 100 million years. Maybe we have to worry about those if we actually survive long enough. Okay? But if we get past those ideas, what do we start doing at that point? If we talk about, if we worry about civilizations, really advanced civilizations, what do we start doing when we get out to that point? If we actually survive for a few 100 million years, what do we start thinking about at those points? Well, Dyson suggested, Freeman Dyson, a physicist at Princeton, suggested that if we really needed that much energy, we could start taking the planet apart and build a shell around the sun to capture all of the sun's energy for use of our really advanced technological civilization at that point. It's called, I will make a point here actually, it's called a Dyson sphere in most literature, but it's actually not a solid sphere. It's actually a network of satellites orbiting the sun at the same distance that Earth is, blocking out most but not all the light. A shell could not be built for some fairly good reasons. But people actually think of it as a shell, as a solid shell, even though that's clearly not what Dyson meant in his first paper. If we don't build the Dyson shell, though, in a billion years, we're going to have to start worrying because the sun's luminosity is going to start increasing. The sun's luminosity will increase by about 10% in a billion years, probably making life on Earth impossible at that point. Maybe, maybe not. Certainly in several billion years, the sun will swell into a red giant, hundreds of times its current luminosity. We'll have to move the Earth away 10 times farther away from the sun than it is right now, at least, in order to keep life on there. Well, people have speculated about how to do that. It's kind of the inverse problem of impacting giant comets on the Earth. People have actually speculated on taking big things like asteroids, passing them close by the Earth, and deflecting the Earth's orbit so that it actually moves out farther away from the sun. It takes a lot of energy. We would effectively need all the energy that the Earth receives from the sun on average over the next billion years to do this. So I think we better start early. But people have actually speculated on this being possible. If we make it past a billion years, a few billion years from now, the sun will die out. It'll swell into a red giant, die out in about 5 billion years or so, 4.5 to 5 billion years. We move to another star system then, right? But in 1 trillion years, all the stars are going to die off. What do we do at that point? Well, I think what we have to do at that point is basically the only things left in the universe by that point are going to be the black holes. black holes are not, of course, all-devouring monsters. You can actually get energy out of them. If you toss things into them, they're actually very efficient at extracting energy out of objects you toss into them. In principle, you can actually get half of the rest mass energy, 1/2 of mc squared, out of any object tossed into the black hole through either heating the accretion disk or through gravitational waves or through weirder processes like the Blandford's Nyack process or things like that. So we can power the civilization with black holes until all of them evaporate, roughly speaking, a Google years from now. 10 to the 100th years from now is when the largest ones in the universe are going to evaporate away. So my posit is, if we work hard and start it right now, maybe the human race can last a Google years. All right. Thank you very much. I would like to acknowledge everyone who's helped me with this before I sign off. Vicki Kern, my editor, and Quinn Fusting and Jessica Pauline at Princeton University Press. The students who took the class that this book was eventually based off of, the science fiction writer Larry Niven, who very graciously let me use the quote that begins the book out, and of course all of my hosts at Microsoft here and at the bookstore sponsoring the event, Ken Ricketts bookstore. Yeah, thank you. So thank you all very much for coming here. Take any questions. Yes?
So what science fiction do you particularly like? Do you like the stories where the writer takes a law, breaks it, but then remains consistent with the remaining laws and whatever laws they've decided to write?
Yes. Actually, that's exactly what I like. David Gerrold, the science fiction writer, who is the author of the Star Trek episode "The Trouble with Tribbles," wrote that if you look at stories, good science fiction stories will typically involve one example of what he called bolognium, one place where the writer breaks the laws of science fiction. And beginning authors should just put one example of bolognium in their stories. Experienced authors can use 2. But only the greatest grandmasters can actually put 3 pieces of bolognium in a story and expect it to be still decent science fiction. So I agree with it. That's actually kind of the criterion I also used when writing the book as well. So yeah, I absolutely feel that if you actually vary one of the physical laws, you say people invent a way to travel faster than the speed of light, you should probably respect the other ones. Because varying one is going to give you enough for story ideas. Yeah.
I particularly like Futurama. Did you see a lot of breaking the science laws in that show?
Futurama. Only 10 or 12 per episode, I think. No, I love Futurama. I mean, look, again, please don't make the mistake of thinking that I'm going to insist that every piece of science fiction must be scientifically accurate. There's a lot of science fiction and fantasy that I like that is not particularly accurate. I happen to like the stories best that don't vary a whole lot. But yeah, Futurama is an interesting example. I mean, someone's paying some attention because you actually do see some interesting scientific ideas presented in it. But you know, they basically bend them to make the stories funnier. I mean, that's really what they do there, and I got no problems with that. Yes.
What do you think about wormholes or dimensional travel?
Wormholes and dimensional travel. That's the piece of bolognium I put in the book. My gut feeling is that faster than light travel is not possible, simply because faster than light travel always involves time travel back into the past, at least from somebody's point of view. You have all this. You also have to have this weird form of unobtainium called exotic matter in order to thread the wormholes through. I tend to think that they're probably not possible, and even if they are possible, they're so far beyond what I can imagine our civilization doing that it's going to be a long time before we can actually even think about things like them. But I would say not proven to be impossible. Certainly not proven to be impossible. If there is any way of traveling faster than light, it's probably doing something like using a wormhole to do that. They seem to be on the very borderline of what the general theory of relativity allows, as I understand it. But which side of the borderline they fall on is kind of, I think, probably anyone's guess. Hawking doesn't believe in them. Doesn't believe that, in fact, you can actually use them for faster than light travel. But again, I don't know where most of the physicists actually fall on this particular case. I'm not a relativist, so I'm not a specialist in the general theory of relativity. So it's hard for me to state with certainty what most people think about that. Yeah.
So, sorry. So building on what you were saying with the general theory of relativity, a lot of our, most classic and well-loved science fiction stories tend to sort of just ignore it completely. They try to treat it in the sense that, well, okay, all of our viewers are either not educated enough or they have some form of like suspension of disbelief, Star Wars, Star Trek, anything like that. So anyway, what I'm getting at is I'm sort of interested in your take on why we, are so enamored with this idea of applying some of the things that we see in our observable world, in our low energy world, to this broader scale where that's like completely impossible.
That's a very good question, actually. Why we actually want to do these things? I think it's because we like stories to be human-sized. If I had to make a statement about that, if you look at most science fiction stories center around things like interstellar discoveries. The Mote in God's Eye, for example, is a very good story about the first contact between humans and aliens called Motes. And so there's a story there. Basically, it's a very good novel. It's a great novel, but it involves essentially this kind of Napoleonic era intrigue involving humans discovering these aliens and the aliens hiding a big secret from them, and trying to figure out diplomatically what the aliens are going to do, what the humans are going to do with the aliens, and vice versa, whether they're going to get involved in a war or not. That's what I mean by, I guess, human-sized stories. We tend to think of these dramatic stories as ones involving, warfare or people falling in love with each other or jealousy or things like that. The cosmological stage is pretty large when you want to set stories like that up against it. If we want to have stories involving humans, then we have to posit things like, if we want to involve stories involving humans interacting with each other, then we have to have things like faster-than-light travel in order for us to be able to actually get out there and interact with the aliens on that level. I will state that not all science fiction writers actually follow along that track. There are writers like Stanislaw Lem, or my personal favorite science fiction writer of all time, Olaf Stapledon, who wrote back in the 1920s, who actually adopt a much broader view of what the potentials of science fiction are. Olaf Stapledon, for example, wrote a novel called Last and First Men, in which he views the entire history of the human race from the present time to an era billions upon billions of years in the future in fairly broad swatches. And he talks about these issues involved with science. And Olaf Stapledon knew his science. He was a journalist, but he actually understood the science of his day pretty well. In particular, one of the greatest discoveries of that time, which is the issue of the expansion of the universe. And so he knew his science very well, and he incorporated fairly accurate astronomy and cosmology into these stories to make these stories set against a real cosmic backdrop. And so he's one of the people actually that did kind of these very much larger than sort of human-scaled stories. But I think the reason we want to do these things is so that we can actually present stories that, in some sense, people are sympathetic with, that we can actually kind of understand the people's motivations in there. Because when you're talking about things that go on for millions of years, it may not be that possible. That's my take on it, at least, why people tend to do that. Yeah?
Interesting. You spoke quite a bit about travel and movement through space. One of my favorite authors is Card, and he has this interesting notion in Ansible and the idea of communication. So while he tries to respect these ideas around travel and relativity and some of those kinds of things, he has this concept of some of that can be defeated through more instant and much more scalable forms of communication across great distances. What do you think about stuff like that? I mean, do you address some of those sorts of things in your book? Or?
I do, actually. I do actually talk about the Ansible, which both Ursula Guin and Orson Scott Card use in their books. As I understand it, the Ansible is based upon the idea of wave function collapse. The idea that if you make a measurement, okay, backtrack for a second here. In quantum mechanics have systems of correlated particles. If we have a system which has net spin 0, and we if we have a particle which has spin 0 and it decays into, say, two other particles, which both have spin associated with them, because you need to conserve angular momentum, one particle will have spin up, the other particle will have spin down, and they go off in different places. One particle must have spin up, the other particle must have spin down. And if you have an observer here who measures one that has spin up, he knows that the other observer in Alpha Centauri, when he measures it 4 years later, is going to measure spin down. Okay, or if you basically send these across, basically, let's have someone in the middle here. You send it to someone a light year that way and a light year that way, the two particles. The guy over there, when he measures the particle being spin up, he knows immediately that the other particle's got to be spin down because he's made the measurement. Now, that would be okay if they hadn't assigned spin beforehand. But quantum mechanics tells you that, in fact, until you actually make the measurement, the spin doesn't have a good value. And so somehow, by making the measurement over here, you've caused the spin to have that value over there instantaneously, whatever that word means. Instantaneously is a dirty word in physics, because it doesn't mean the same thing to everyone. And Ursula Guin had this idea of using this effect for her communicator. I don't know if it's original to her or to Card or who actually first thought it up. But in any event, the problem with that is that the measurement that you make, there's no way of actually putting a value onto the spin. It is completely indeterminate. It could be either up or down. If you make the measurement, then you know the other guy's measurement is either up or down. But in a physics sense, no information has actually been sent because what you're receiving is, if you look at these, if you make repeated measurements, you're receiving a random set of ones and zeros, called one spin up, zero spin down. You're receiving a random set of bits here, and there's actually no way to send an actual intelligible signal using that. This is actually stuff which is at the forefront of atomic physics right now, my own field of study, because correlated systems, you can actually do pretty neat things with correlated systems. Quantum computation, for example, is based around these ideas, but it does not appear to be able to transfer information faster than the speed of light. Yes?
Did you consider anything, or what are your thoughts about like hibernation in space travel? So we don't have to talk about great speed, but different problems?
Sure. I did not actually consider that in the book. If I ever write another book, I'll probably actually include that in there. It was one of these things where the book was getting a certain length, and at some point you have to say, that's it for it. Yeah, you could actually put people in suspended animation for, well, maybe you can put people in suspended animation for very long periods of time. You're talking about, however, if you're talking about any sorts of reasonable speeds, you're talking about periods of time which are much, much, much longer than recorded history. If you look at the speed, for example, of the Voyager spacecraft, I think that people said they'll get to the distance of Alpha Centauri. They're not heading in that direction. They'll get out that distance, the nearest star system, in something like 40,000 years. So it's a possibility. I mean, one issue with all of these projects is that, as someone who's funded by the government, you have to worry about funding for projects like this, because if you're talking about a project which is going to have, even talking about projects that have payoffs in 20 years is kind of dicey as far as getting, as far as actually funding these. So you actually have to posit a very different society than the one we live in. As far as I know, there's nothing intrinsically impossible about that. I may be wrong, again, because I'm not a biologist, but as far as I can think of, there's nothing intrinsically impossible about long-term suspended animation. Yes?
I guess a lot of the science fiction early years inspired some of the innovations, like Heinlein's books inspired our trips to the moon. I think maybe the replicator is inspiring 3D printing. What ideas are you think are going to inspire the next generation of technology?
Sure. I don't know the historical pathways involved. It's a good point in that I think that I think the most direct example of this is that Arthur Clarke had the idea for the communications satellite back in the, I think, 1948. This idea of putting satellites around the Earth in geosynchronous orbits to do satellite communications. He actually refused to patent the idea, basically, as a present to mankind. But he had this idea. It was printed in a paper. He actually printed it up in a paper. And I think that's a very direct inspiration for, this is the idea for communication satellites that he had. The path between other things like that, I think, is not quite as clear. If you look at, I don't know the history of the space program well enough to say how much of it was inspired by science fiction, how much of it was inspired by scientists who were not initially even inspired by that. Well, I take that back. Wernher von Braun, of course, has made statements in fact that he was actually directly inspired by Jules Verne and H.G. Wells. So I think there's actually a lot of value in what you just said. I think that in fact science fiction can actually serve as a great inspiration, even if the scientific ideas aren't particularly good ones. I think actually there was I saw a TV program once where the guy who invented the MP3 format for music playing said that he was actually inspired by Star Trek The Next Generation, where they would actually call up a bit of music or something like that and play it from the computer. And he was basically inspired to develop this because no one had done, it looked like a great idea and that no one had done this. But I think that's a very good point, though.
I think we're out of time.
Okay, well, thank you again for coming.
Thank you.